Is everyone happy with the course so far? I think that was a yes. Can anyone tell me what these places are? Rotorua. Waiotapis. Yes, well done. And the other one? Very good. You're familiar with museums. Okay, so last week we looked at the four deposits that formed in magmatic settings. This week we'll be looking at deposits that formed from hydrothermal fluids. And today we'll be looking specifically at those deposits in which the fluids were derived from magmas. So we'll just briefly look at the occurrence and the tectonic settings where these deposits occur, the fluid origin and some properties. We'll have more on fluids next Wednesday, and then we'll look at a bit of detail to view deposit types, porphyry, grisons, skarns, and epithermal deposits. And for those of you who might be interested, these are treated in Chapter 2 of Introduction to Ore Forming Processes and Chapter 3 of Ore Deposit Geology. So as we said, magmatic hydrothermal ore deposits are those formed from precipitation of metals or minerals from aqueous fluids or vapor. And the origin of these fluids is magma. We'll treat in this lecture. Other sources we'll treat in the next lecture on Wednesday. And these are often sources and the main deposits for copper, gold, molybdenum, tungsten, and tin. Map. So the red spots is where this type of ore deposits are often located, and what is striking about this? Or the distribution. What's the association?
500.
Speak up. Subduction. Oh, damn it. Yes, exactly. Subductions or continental collision or suture zone. So subductions, for instance, here in the Western Americas, or the Western Pacific, Philippines and Indonesia, New Zealand is a spot as well. Or here where basically Africa, Arabia and India collided with Eurasia and basically formed through subduction. So yes, as we said, the link between all these settings is a subducting plate. Whether we have a continental type subduction zone or an intraoceanic subduction zone, we need a slab that is subducting and it introduces metals into the mantle and also volatiles. So as the plate subducts, we have the mafic minerals, olivines and serpentine that basically transform into amphiboles. And later we have the breakdown of amphibole, which causes dehydration. And in addition to carrying some metal contents off into the overlying mantle wedge, these fluids also, the water released by the dehydration breakdown of amphibole, allows the mantle wedge to melt. It reduces the melting temperature. And you should be somehow familiar with this process. So the fluids we are dealing with are mostly water, and this is a phase diagram for water, where we have temperature, pressure, and water in the liquid state, in the vapor state, and in the supercritical state. However, the water we are talking about is dissolved in the magma, so we don't have two separate phases, magma and water, but we have water that comes dissolved in the melt. And as you can see from this diagram here, we've got now pressure and water content and different types of magmas, basaltic, andesite or granite. We can dissolve quite a lot of water. For instance, 10 kilobar, which is about 33 kilometers depth, basic magmas, basaltic or andesitic magma can dissolve about 10 to 12% water, which is quite a lot. So as these magmas are formed in the mantle, they contain water but in a dissolved state. However, in order to form more deposits, we want to separate the magma and the water. And there are a couple of ways of doing that, and they are called first boiling and second boiling. First boiling occurs by decreasing the pressure, so Coca-Cola bottle type experiments. As you open the Coca-Cola, the pressure inside decreases and you exhaust the gas. Same thing happens here. If you place a magma body shallow in the crust, you reduce the pressure, and so you allow the water to basically dissolve and form fluids or vapor. A second way of separating magma from water is by increasing the water concentration, basically, through fractionation. So if you start with a basaltic or andesite melt and you start crystallizing, let's say, olivines or pyroxenes, they are anhydrous crystals, they don't entrain any water, and so the water will remain enriched in the melt. Up to a certain stage where if you basically move up, you're enriching the melt in water and you cause it to saturate and separate. And once you have a melt, a magma, and watery solution, you can start to scavenge the melt in the metals that we are interested in. And although some elements, or most elements we are interested in, are not readily soluble in water, if these fluids contain salts, they can form ligands, and hence these will form complexes with the metals and will actually scavenge the magma, the metals from the magma, such as, for instance, chloride scavenges copper from the melt. Another one, copper forms a complex with water and ammonia. So once we have these saline aqueous solutions that contain metals as complexes, we can remove them and make them precipitate the metals that we want. Now the thing that happens is when we separate the melt and the water, we increase the volume. And so suddenly we have a system that was at volume X. At one stage we separate the water, the volume increases, we have to allow that to escape. And that often occurs and creates brecciated areas above magma bodies, or in this case veins that are then infilled by quartz or carbonates. And I should point out this resource here. It's a book with a lot of very good pictures of ore texture and deposit images, and this is available on the library website. It's available online. There is an older version of it in the library, you can have a look, but I recommend you just go and download the PDF of this one. And once the fluid flows through the country rock and they form veins, we've got basically precipitation of ore minerals in these veins, for instance here, pyrites and chalcopyrite and quartz, or also disseminated within a porous and permeable country rock. And that's basically a process that results in orogenesis. And as you can imagine, when we have basically tons and tons of fluids migrating through the country rock, well, these will basically affect the form of the country rock. Because when we have fluids, they like to equilibrate with whatever medium they're flowing through, and so they react and they form alteration mineral assemblages. And these can extend from centimeter to kilometers at field scale. And basically different conditions result in different alteration assemblages. And here are just examples of advanced argillic, PHILLIC, ARGILLIC, PROPYLITIC and POTASSIC alteration zones. And as you can see, different mineral forms at different conditions. And these are often used as exploration vectors in mineral exploration, because they occur at different zones within deposit site. And that depends on pressure, temperature, fluid composition, and the host rock composition. And as I said, different mineral assemblages characterize each of these zones. So we go from a potassic zone close to the intrusion, to an outer PHILLIC zone, to a propylitic zone further out. And as you can see, the different the boundary between the different alteration zones also coincide with different ore shells, with high-grade shell here, and pyrite shell in the PHILLIC zone. And just a few images. These are from the book that I told you about. For instance, the potassic alteration forms at relatively high temperatures. So it is related to the core of the system near the intrusion. And it's characterized by the formation of alkali feldspar and biotite through the addition of potassium from fluid. And it can be quite tricky to identify, because if you start with a rock that is already feldspar rich, we might need to look at micro-textual studies to identify whether there was indeed addition of potassium from fluids. The PHILLIC alteration is a bit further away, so it's moderate temperatures. It occurs around the capping zone of mineral deposits, and it's caused by acid fluxing through the rock, and acid like to leach or remove these mobile elements, potassium, sodium, and others. Then we have the formation of white mica that replaces alkali feldspar, so quartz, chlorite, and pyrite. The propylitic alteration also occurs at moderate to low temperatures. It occurs at the margins of the deposits, and it's characterized by apidol chloride calcites. That occurs by the addition of water and CO2, carbon dioxide, to the original rock. And finally, the argillic alteration, which is basically the low temperature surface alteration. It's caused again by acid flux, which breaks down feldspar to clays like kaolinite and smectite. As you can see, all the white in this rock is basically feldspar that is deceased, and it's now mica, clay. And alteration can lead to some spectacular landscapes, where we have here propylitically altered igneous rock, which is capped by acid leached rock in Colorado. The place is called Silverton, probably because there were mines. So moving on briefly, or a bit more detail maybe, on porphyry deposits. These are generally related to I-type intrusion, so igneous intrusion, well, igneous granites, so-called granites that are derived from direct partial melting of the mantle. And we can have two types, copper-rich or molybdenum-rich deposits. Starting with a copper-rich, we have an intrusion that reaches relatively shallow depth in the crust. And so the decompression basically causes the separation of magma and water. So we have first boiling. And because we have boiling that occurs relatively early in the crystallization history of the magma body, the melt is still rich in copper. So the fluid basically are able to scavenge the copper from the melt and transport it further up if it's precipitated. If the intrusion, however, does not reach the same depth, same shallow depth in the crust, so it stalls at a deeper level, we don't have this decompression boiling, we don't have first boiling, so we start to crystallize more and more of this magma. And copper, through sulfide crystallization, starts to crystallize and go in the crystallizing portion of this magma body. So we leave residual melt that is enriched in molybdenum with respect to copper. And so once we have crystallized enough of it, we have the second boiling event where water is enriched through crystallization. And at that stage, the fluids will basically scavenge molybdenum over copper. Is it clear? An example of a copper porphyry deposits is Bingham Canyon in Utah, I believe. And this is hosted within a equigranular monzonite, but the mineralization was related to a later intrusion that formed porphyritic rock. So these rocks, these deposits are called porphyry because they come related to porphyritic rocks. So as you can see in this reconstruction, we had an igneous system that formed a volcano, several intrusions that might have been magma reservoirs, and a later intrusion that basically introduced the oil-forming fluids in the system. And I recommend you go and read this article that you can access through the library website on economic geology, the journal. And if you want to know in detail how this formed, there is a good history in that one. But briefly, basically we had the first intrusion, set the scene. Second intrusion, porphyritic came along, introduced a lot of fluid, and due to the build-up of fluid pressure here at the top of the reservoir, basically this caused doming of the system. And when you have doming, you've got increasing in volume, but you kind of retain the same mass. And so you allow all this fracturing. And the fracturing is where the fluids can percolate and precipitate the copper or the gold. And this process occurs again and again, several times. And this is what Bingham Canyon looks like. It's probably one of the deepest mines in the world. When you've got something very deep, nature wants to fill it in, and so you've got collapses, as the picture in the left or right hand side shows. And as you can see, the deeper you go, you've got grey rock, which is the original igneous unaltered rock. But further up, and especially the landslide, you've got all these leached and altered rock, which is less stable and tends to collapse. Another way of looking at ore deposits is this so-called paragenetic sequence. And this is from a copper deposit in China. So you've got well, at the bottom, cross-section of the geology of the area. At the top, we're not too concerned about the major element variation. What is interesting is ore type. Here we have the legend with veins and dissemination on the sides. And then the ore minerals and the alteration. And as you can see, close to the igneous body, we've got high temperature mineralization, pyrite, copper, molybdenite. And as you go further away from the source of the fluids, we've got sphalerite and galena that are ore minerals of zinc and lead. And we will see some of these in the lab tomorrow. And also the alteration zone with different distances from the deposits corresponding to different mineral assemblages. Another way of looking at it is by looking at the timing of all these occurrences. And here we've got a list of minerals, and we go from late magmatic hydrothermal fluids through to supergene, which is fluids that are unrelated to the magma. It's caused by percolation of meteoric water, and we will actually see that in more detail in the 5th lecture. But again, different